a presenter on the official laptop.
Don't know where that's
Could I
gone.
use that one?
Has anyone got the presenter thing? Yeah. Sorry? Yeah, there was one. I don't know why.
Oh.
He's got one in the back. Here's the laser. Ah. There we go.
Just put a laser at least.
Okay, so first of all, I want to thank the organizers for inviting me to this really nice place and to give me that I've been given the chance to present parts of my work. And of course, it's not all my work, but it's together with colleagues from Germany. And I'm sorry that actually in the program title wasn't announced, but I sent my abstract like 1 month ago, so something got wrong, and I think it's not so bad. So I will speak about discontinuous Galerkin methods, and of course here the interest is atmospheric flow, but you can also use this for other types of problems. So projects I've been involved in the last 3 years is mainly part of the DFG priority program Medstrom, and there the sub-project is adaptive numerics for multiscale phenomena, and this is a cooperation with Slavko Prda, Andreas Dedner and Dietmar Kröner from Freiburg. Andreas now is in Warwick, and Michael Baldauf and Dieter Schuster from the German Weather Service. And the idea was to study adaptive conservative methods for atmospheric problems. And of course, we look at the classic set of test cases. So of course, we cannot do really weather forecasts with our software, but we can compare with what's the weather service is doing. And we really think got a bit further in this step. So another project I've been working on is the simulation of two-stroke engines with detailed chemistry, and of course the underlying PDE solver is just the same. Yeah? So we can use the DG solver we developed, we can use for both problems. So here this work is with also with Andreas, with Mark Fein, Dietmar Kröner, Dirk Lebitz and Martin Nolte. Okay, so the model problem I will look at throughout this talk is some sort of convection diffusion equation where R most of the time is the identity, F of u is a convective flux, A of u times gradient u I call a diffusive flux, and S is the source term, and omega is the computational domain, and T is the simulation end time. So that's the setting. The DG method I will present is developed for this case, and whatever you can fit in here, the method should somehow work, okay? So one example is the compressible oil equations for an ideal gas. As I said, R of u is just the identity. U is the classic set of conservative variables. F is, in this case, the standard Euler fluxes. A of u is 0, and also no source term is available. So that's one toy problem I've looked at a lot. And there are a couple of other problems we cast into this framework, and we applied our DG methods for. So like transport equations, of course compressible Navier-Stokes, MHD would work, shallow water equations, two-phase flow and porous media. Okay, so that's a short outline of the talk. I will first introduce the DG methods for these sort of problems, then, and this is pretty much the work that I did, I will comment on parallelization and efficiency of the method on today's many core systems. And this will, for example, also include, okay, this is not on many core systems, but we also have done a comparison with the classical finite difference methods for these atmospheric test cases, and maybe in the end a short comment on the software behind all this. So the G method on one slide here. If we come back to the Euler equations where we just have this convective flux here, then the DG method is really easy to derive. You choose your discrete space, which is just consisting of polynomials, piecewise polynomials, on each element of your discretization grid, which is G here. And then you multiply with the test function, you apply integration by parts, and on the boundary of each element you have to come up with the clever choice of a numerical flux. And for these, for example, for the Euler equation, this is not a problem because you already know good numerical fluxes, and these are those you know from finite volume schemes. So any numerical flux that works for a standard finite volume scheme you could use here. And the usual properties you would like to have is consistency, Lipschitz continuity, and conservation. So one nice thing about the DG method is that if you look at the stencil of the method, so you want to compute the fluxes and these integrals on, whoops. You want to compute these fluxes on the element E, then usually the stencil of the method is just including the neighboring elements, and this is a really appealing feature, especially for parallelization. If you choose your discrete space consisting of constant polynomials, then you see this term here drops out, and what you get is just the standard finite volume method. So that's the relation to the finite volume methods, and you see the stencil just is the same as a first order finite volume method. Okay, once you got the spatial discretization, you plug it into the equation, you get a system of ODEs, and you apply the really well developed strong stability preserving Runge-Kutta methods. So another advantage of the G methods is that you don't have to invert a global mass matrix, since the basis functions are discontinuous. So that's a big plus. You have a high data locality once you go to higher order. I will come back to this later. In our setting and throughout the talk, if I talk about implicit schemes, then they are based on Jacobian-free Newton-Krylov methods with a matrix-free implementation. So matrix-free implementation, keep that in mind, please. That's an important part. So this just means that if I apply a matrix vector multiplication, this means I have to iterate through the grid and evaluate the whole operator. That's a bit more expensive in terms of computation, but it's much more easy to implement, since in these cases the operator can be quite difficult. So matrix free, I just don't want to set up any big sparse matrix, whatever. Okay. So if you're talking about nonlinear problems, then for the DG method, if you go to higher order, you have to come up with some sort of stabilization, otherwise the method won't work. And there are, to my knowledge, at least three kinds of stabilizations you can do. One is the artificial diffusion. There are several groups that are working on that, and I didn't mention here the group of Frank. I know they also use this kind of stabilization. we decided at the early point not to use that, because if you do that, you have to add some sort of a diffusion discretization to your discretization, which I didn't talk about yet. The nice thing though is you don't have to change anything for your implicit scheme. Okay, so that's a plus and a minus here. Then you could do something like HP adaptation or polynomial order reduction. Whenever you discover problems, you can go back to 0 or to first order, and then you know the method is stable. So there's a work here by Andreas Stedner, Babis Makridakis, and Mario Olberger for a scalar problem where they prove some theoretical error estimate and where they show how this could work. But the problem here is that this is really costly. So maybe for 3D Navier-Stokes it's not yet the right thing to do, but it's an idea. So what we did then, of course, was to implement some sort of a limiter stabilization, and here the nice thing is that you don't have to add any extra terms in the equation, but at least I had some problems with the implicit method. Okay, so usually what you want to do is you apply the stabilization to the convective terms, and then you use some sort of semi-implicit solver to get along with this. So limiters, there's really a lot of papers, and I only mentioned a few. So if I didn't mention anybody here, sorry for that, but this would be more than one slide. There's a lot of work from Coburn and Shu, Krivo-Donova and co-workers. Beatrice Rivière did some works, and here also on non-conforming methods, on non-conforming grids, which you don't find that much. So most of the work, they do some experiments on Cartesian or maybe triangular grids, but the problem we were facing is that we want to have limiter-based stabilization for non-conforming methods, since we want to apply adaptivity, and in this case non-conforming adaptivity. So that's why we came up with yet another approach. And the nice thing about our method is that it works on 2D, 3D grids. It's not geometry dependent, so you can use it for hybrid, non-conforming, even Cartesian grids. So that's the nice thing. So the basic idea is you replace your original spatial discretization by something that's called a stabilized discretization, and this operator can be constructed element-wise, since your basis functions are discontinuous. This is the way to do it, and so the big question is how to construct such a stabilized solution on an element, and of course, once you do that, you want to make sure that the new solution fulfills some desirable features. So one of them is in regions where the solution already is smooth, you don't want to do anything, because that's the best thing you can do in that case, and this requires, at least in our setting, some sort of a shock detector. And in the results I present here, this is the one based on the work of Krivo-Donova and co-workers. So if I have to do something, then I at least want to have that the mean values of the solution stay of the old and the stabilized solution stay the same, because they belong to the first order scheme, which was already stable. At least at the quadrature points I'm going to evaluate the stabilized solution, I want them to be physical, for example, density positive, and so on and so forth. Okay, I didn't tell you that we always only reconstruct linear functions, and if we do so, we require that linear solutions are reconstructed exactly, of course.
Does that mean that you're restricting your entire method to linear?
I will come back to that. We require a minimal stencil, and this is that has to do with the parallelization and also with our grid manager that we have currently available is restricted to ghost cells, so you can only have neighboring elements. So any method that would use a larger stencil than that would be very complicated to implement. Yeah.
Is neighbor on the face or only as a
Neighbor on the face.
face?
Yeah.
Direct neighbor.
So for the DG method, we don't require neighbor over vertices, which you would, for example, require in a standard finite element, continuous finite element set, which is a bit more complicated.
Yeah, but some people for choosing the stencil for slope limiter use the vertex neighborhood instead of the edge neighborhood. So neighbors that touch the vertex instead of, you know what I mean?
Sorry, I didn't understand the beginning of the question.
No, I just when some people choose their stencils for slope limiters in DG, they don't. I mean, it's true you only need the edge fluxes, but sometimes people choose a stencil that includes the
But
vertex.
in this case, we only choose the same stencil as the method already had. Okay, so that's basically the idea.
No extra data.
No extra. Yeah. And of course, monotonicity. So the reconstructed or the stabilized solution should have the same monotonicity properties as the mean value on the neighboring cells. So basically, as the first order solution. And then, what you do to get the stabilized solution. So once you detected that you're somehow in trouble or your solution seems to be unphysical, you reconstruct a new solution which is at most linear. Otherwise, you just go along with the DG solution you already had. So that's basically how it works. A nice thing about this is that you can choose your ansatz space to be constant. You can choose your reconstruction space still to be linear, and you just have a standard second order finite volume method. So you got both options here. And then what you do is just reconstruct on every element, and you get a higher order finite volume method. And this has been tested in, for example, in shallow water flow and so on. This really works quite well. Okay. So how does the reconstruction work? And by reconstruction, I mean we do, most of the time, we do the reconstruction. You could also only limit the DG solution, but we found we get better results if we also include the reconstructed linear functions in the set of possible stabilized solutions. So what you do in this non-conforming situation, so the circles here are the mean values the linear function is constructed of, and the crosses mean we have to make sure that they, with these two mean values that there is no oscillation. So that's basically how it works. So you do it for all combinations that you got in this case. You do a limiting, which is basically min mod super B, what you like, what you know from theory. And in the end, you choose the new approximate solution to be the one with the steepest gradient. So you have a set of linear functions that you could use, you limit, which basically restricts, or you throw out some linear functions, and then from the set of functions that's left, you take the one with the steepest gradient. And there's a publication together with Andreas Detner in Journal of Scientific Computing published last year where everything I just said is described. Okay, how does this work? Here is, we did a lot of test cases, EOC studies and so on. Here's just one test case that's at least a standard test case for the Euler equations, the so-called forward-facing step, where you have a initial state, constant initial state, inflow on the left, reflective boundaries here in green, and outflow on the right. And the density pattern at time equals to 4 should look something like this. So here's are some comparison on a resolution of 1/160 on a Cartesian grid. So that's the standard finite volume scheme, the second order finite volume scheme, the second order DG scheme, and the third order DG scheme. And now coming back to the question, only in the regions where the shock detector detects a shock, the scheme is reduced to linear, at most linear. In all other regions, we keep the original order of the scheme. Yeah.
Does that mean that you reduce that you fix the polynomial order in those cells to like order 1, like with polynomial adaptivity, or you just zero out the higher order modes and then let it go back?
When we did these computations, we zero out the higher moments, but nowadays we could also do HP adaptivity. But it's a bit of a, I mean, it's more difficult to implement this, but to do these calculations, we just zero out the higher order moments.
So is there any P gradation, or so you really just drop from, I mean, I guess at third order it doesn't really matter, but if you were just quite high order, you suddenly go from like a degree 7 cell to a degree 1 cell.
Yeah.
Do you not anticipate that being a problem?
I
do you anticipate the higher order modes just bouncing off that interface?
I think in these near shock regions, you're in trouble anyway. So, I mean, we haven't really tested the really high order. So that's here P or K2, which is third order, but we did also K3, but not more than that. Yeah.
Another way of asking the same question: when you reduce the order of one cell, do you find that that leads to a reduction of order in subsequent time steps in neighboring cells?
I really don't know.
Well,
I
you
mean,
have first order error with the shock limiter because you're shock limiting here, so
that's
you're getting pollution around that area.
To be honest, I would have to speculate. I didn't really look into that. So let me come back to adaptivity. So here, that's the same example, and what you see in the following movie is here you see the shock detector, the density, and the adaptive grid. So green means this, you're using the original DG scheme. Red means the limiting has been applied and the scheme is at most linear. So you can see that in most of the regions you can really use the original DG scheme, and stabilization is only applied in the strong shock regions. Yeah. So in the beginning, what's the white thing here is the uniformly refined grid, and if you do adaptation, you get a factor of 6 less elements in this case. And this is a non-conforming triangular grid, by the way. So the adaptation indicator that was used in this case is pretty much the same as the shock indicator. So whenever we discover a shock, we also want to do age adaptation. Yeah. So we reduce the order, but also we increase the spatial discretization accuracy by doing age adaptation. So that's sort of the strategy.
What order does that happen in? Because surely that matters, right?
Sorry?
Well, if you can either decide to degrade the order in one big triangle and then cut the triangle up, or you can do the reverse. And if you did the reverse, presumably you wouldn't make the same choice all the way across the big triangle.
I mean, I think there are several approaches, but that's just one idea how to do it. And the thing is, I mean, we prove that this works in 3D, and this result I'm presenting right now is like 4 years old. So since then I haven't really done much 3D adaptive calculations, but I will come back to this in the future. So what we could do back then was this is basically the same problem in 3D on a fully unstructured grid consisting of hexahedrals with the quadratic polynomials, non-conforming refinement, including dynamic load balancing based on Midas and Parmenides, and here the final grid consists of 4.5 million grid cells. If I would refine uniform, I would have had 95 million. Here's some statistics. Adaptation takes about 5% of one time step. And if we do load balancing, it's about 10 to 15% of one time step. But we only have to do that approximately every 100th time step. And here are some scaling numbers. If we go from 128 to 512, we have an overall efficiency of 93%, strong scaling here. If we only look at the ODE solver, it's even better because some of the critical parts are left out. So just to give an idea how this looks like. So you see the density up here from below and above, or from, yeah, and the adapted grid with the partitions down here. So you see there's quite a lot of rebalancing going on, but it doesn't really degrade the efficiency of the overall method. So that's basically what we had or what we have for convection dominated problems. Now what happens if you look at the compressible Navier-Stokes equations and here in the theta form? So you also got this Euler fluxes here, and then you got some diffusion-like or viscosity-like terms here. So we're still looking at this equation, same framework. Now, how do we treat this term is the question. And basically we do the same thing. We just have to come up with additional numerical fluxes, and in this case 2 numerical fluxes, A hat and U hat, for the diffusion terms. And the rest is pretty much the same. So we again use IMAX, so implicit, explicit, or IMAX SSP methods. In this setting for the convection diffusion case, now the big question for us was how to choose A hat and U hat, and one choice has been presented by Mark Ainsworth this morning, is the interior penalty method. There are several other methods we tested, and I will briefly introduce them. So one thing you can already see, if U hat equals just the average of U, then the whole last term drops out, and that's a nice feature. So you can get rid of this term here if you just have a U hat flux looking like this. So we tested and implemented and compared these 5 methods. So it's the interior penalty, the LDG, BR2, CDG, and finally we came up with a new method called CDG2, since we figured out that's a bit more efficient than all the other ones. And I think I don't go too much into the details. Maybe one interesting fact. So we got one parameter here in the method, which is nicely computable. So the stabilization parameter in this method and in the new method, but also in the BR2 and also CDG, is such that you just have to count the number of neighbors of an element, and that's basically the factor you have to put into your scheme.
So which one is the best?
I will come to that in a second. I think depends. I mean, you cannot answer this question. I mean, you can never say this scheme is the best. Depends on the problem you're looking at. Depends on how much time you have left for implementation and things like that.
I mean,
okay.
Typically those methods are applied to elliptic problems for
Yeah.
testing, and you're doing this convection diffusion. So
So we did both. So here's just one elliptic test case, and this is part of the 3D benchmark on discretization schemes for anisotropic diffusion problems on general grids. And there you can see a lot of different finite volume, finite element, and DG schemes tested and compared. So that's the grid. That's pretty simple. The problem is smooth, and as we expect, DG does not do so well. So the CDG method here in green, and in orange there's some flavor of the IP interior penalty method, which is basically the weighted interior penalty, but in this case the diffusion matrix was smooth, so it's just the standard IP method. And the thing is, in these elliptic cases, I see that it doesn't make really sense to use linear basis functions for DG. You really have to make use of the fact that you can easily go to higher order, and then you can really gain and outperform the other methods, as you can see here. So this is L2 error here and number of unknowns down here, and you see that giving a certain amount of unknowns with the higher order DG, I can easily obtain better results than for all the low order finite volume methods. So this benchmark also includes a runtime to error comparison, and also here we found that the new method is slightly better than the interior penalty method.
which one is interior penalty?
The yellow ones of different order here. So the yellow ones is a result by Peter Bastian, and he really did the 1 to k equals 4 results, which in the end was a really tough thing, I guess. Okay. So we also did the comparison for the equations we are really actually looking at. So the compressible Navier-Stokes with an analytic. We did a simulation which actually has an analytical solution, which was presented in a paper by Klaus-Dieter Munz and his PhD students. And in this case, we also saw that the method we introduced is slightly better than BR2 and is way better than the original CDG method. Okay? In this case, we didn't compare to interior penalty and LDG, because for interior penalty, for the Navier-Stokes, you have to use like kappa equals 10. So it's not really a theoretical based parameter. And LDG is a different story. And these results were obtained with the IMAX scheme. Again, of course, based on matrix-free and Jacobian-free Newton GMRS. The thing about the CDG2 method is, compared to LDG, that you could decrease the stabilization parameter even further below the theoretical bound, and then what you do basically is the condition number of your system is much lower, and of course the linear solver converges faster, and overall your method is more efficient. So that's the thing. Okay, that's all I want to say for discontinuous Galerkin methods for these kind of problems. Now I like to speak about parallelization and implementation. Can these methods be used to do simulations on the big supercomputers we have today? So in the following half an hour of the talk, I will concentrate on the density current test case. So here you see the picture of the original paper by Straka and co-workers. Here is an adaptive simulation Slavko did lately. Okay, so parallelization means in some sense you have to split up your domain you have to do some computation. So that's your spatial operator again. Maybe that's your computation grid. And if you want to compute the fluxes here in the blue element in parallel, this could be really different. And what we do in Tune is, or in the moment, which is probably for DG not the best approach, we have a so-called ghost cell approach. So for every cell, for every phase on a process boundary, we introduce the neighboring cell as a ghost cell on the other process, which we can use to store the data on these cells to evaluate the fluxes over these boundaries. So this basically means that these fluxes are evaluated twice, once on each process. I don't claim that this is the best way, I just say that's how we do it. And once in a while you have to, or maybe once per time step, you have to do a global OR reduce to get your minimum for the time step. So that's the two sort of communications you have to do. So then usually what you do is each processor computes the element integrals and the fluxes. You compute the local delta t. You communicate the update, which is basically copying the values that you have here to here and vice versa. Or you can do it also differently, but it doesn't really matter. And then you do a global minimization of the time step. So this global minimization of the time step is a bit of a problem, because if you go to higher number of cores, then this becomes much more expensive and so on.
So with many core, you just mean many cores and not a many core chip or so?
No, I mean just like 100,000
cores, okay.
Cores and maybe more. So what you could do, if you have a good guess for your time step, you just use a fixed time step, which is sometimes maybe done in I know that the weather service does it that way, or they have good ideas about their time step, and they can do that. They don't have to do global minimization. Here, another approach is of course local time stepping, but this is really complicated to implement. Okay, so that's the basic scheme, and I went to I ported the code to the Blue Gene P that we have in Jülich, and I wanted to see how good does it work. So here, this example is for an explicit ODE method with a fixed time step, and I wanted to know how well does it scale if I go from 512 to 65,000 on a relatively small grid. So the grid has 243,000 cells with a fifth order method, which means that I in total have like something like 252 million unknowns. And on the 65,000 run, I have something like 2,300 unknowns per core. So this is really a small problem then. And it turns out, it doesn't scale to 65,000. Maybe it scales to 4,000, but doesn't also really scale here to 32,000. That's strong scaling, by the way. So I keep the problem size, just increase the number of processes. And okay, so what I did then is, that's an idea that also Frank has implemented in his code and many other people, and goes back to some ideas in the late 90s. So what you can do, you can overlap communication, computation, and this simply means you split up the computation of your discrete operator by first sending data you need on the other processes. Then you calculate all the element integrals, because no neighboring information is needed. Then you receive, and this is a blocking operation, so maybe you have to wait, maybe not. And then you calculate the surface integrals. You could even calculate the interior surface up here, but for me it didn't really matter. I mean, you will see in a second. And then you just sum up. This is a vector operation, and you are back where you were before and proceed as normal. So this is some ideas you can find in the paper of Keys and co-workers from 1999, and maybe also in other papers. And if you do that, you can scale very well from 512 to 65,000 with an efficiency of 70%, which means that you can really take your problem and push up the number of cores and do the simulation faster than you could before. Yeah. So this is one thing where I think the DG method can really help to calculate bigger problems or to solve problems we couldn't solve before, because we can push up the number of cores here. How does it? And then I thought, okay, now let's try the implicit method, because that's also interesting. And it turns out, again, if I do the same with the overlap of computation, of course I cannot use the fixed time step anymore, since I already got some dot products in the GMRS, so it doesn't make sense. And it turns out, again, it doesn't really scale well. And then I thought, okay, what might be the problem? And in that case, the problem was that the grid wasn't really well balanced. So on some processes here on the fine on the high number of cores, I got 1 cell, and on other processes I got 8 cells, and this really killed the scaling. If I use a space filling curve-based approach where I have almost equal balance on each process, I can scale very well with the efficiency of 75% to 32,000 cores for the implicit ODE method, okay? And this is, again, strong scaling. So if I can do strong scaling, I figure I can also do weak scaling to some sense.
So which of the two was fastest to solution?
I think in that case, for the density currents, I always thought that explicit is probably the better choice. But once you go to finer grids, implicit might be the better choice. Because if you have a diffusion term, somehow this on a fine grid, this kills the explicit method. But I didn't see that. And of course here, so these are the average runtimes, and for the implicit, this is much worse than for the explicit method. Yeah. So that's what we can do with our DG method. So we can basically use machines like the Blue Gene here on a Cartesian grid still. So I'm not back to full adaptive on these machines. Yeah.
So on the implicit runs, can you tell me roughly the average number of iterations?
That's a good question. I would have to look it up, but it's like something like maybe 20.
So that's pretty high. So that's a good result then. It's a very good result.
Yeah, I mean, I really look forward to include what you presented on Wednesday, the matrix-free preconditioning. I think this was what really helped us, because in this run we have just a plain GMRS without any preconditioning. Okay, so that's not the best thing you can do.
That's very encouraging.
I think so. I mean, there's also in Tune we have a parallel AMG solver, which was developed in the group of Peter Bastian, which scales to the full machine to 300,000 cores. So it's not that you can't do implicit on these big machines. It's just really, really not easy, and you have to think a lot and you have to do much work. So this is where the software comes back in, because you can't just rewrite all these things in 1 year or something like that. It's really a lot of work. Okay, so I wanted to present adaptive runs here, but it wasn't on the Blue GP. I couldn't do it. So our code is not able to perform well on these machines, and now I present the reason why. So consider we have this macro triangulation, and during a simulation it got refined like this. then how do we split the load? Currently, we do this by on the macro triangulation, setting up a dual graph using metis or parameters to calculate a graph partitioning and then distribute the macro cells with the hierarchy of cells we have below that macro cell to each process. So that means that our partitioning can only be as good as the partitioning of the macro triangulation is. And this is a big drawback for the many core system, because then you have to have a really fine macro triangulation, and this cannot be used for problems like the density current, because there you compute on relatively coarse grids but many time steps. Yeah. So that's one problem we have with our code, and here's one solution I have to that. So assume we have computed a domain decomposition like that, and the red one is maybe MPI task 1 and the green is MPI task 0. Then what we can do is making use of the hybrid parallelization and come up with so-called micro partitionings on process 1 and process 2, and using this hybrid parallelization to maybe get a better micro partitioning, and such that the macro partitioning we have is not affecting too much of the simulation. And the splitting here is, the idea is just the same as you do in the MPI domain decomposition. Each thread only calculates element and fluxes that belong to his domain. On the boundary, you just compute the fluxes double. This means you have absolutely no data synchronization is necessary. Yeah? So you compute the fluxes twice, but you don't have to synchronize any data. And here's a scaling. How well does this thread parallelization work? So on a AMD Barcelona, if I go from 1 to 16 threads on a grid with 72 elements, which in the end comes back to something like 3,000 DOFs per thread, I get an efficiency of 85%. So this is really okay. I can live with that. And of course, if I increase the number of elements, the scaling gets a bit better. You have to be aware that for doing such simulations, you have to use thread pinning, though, which can be done by a tool called Liquid Pin or maybe Task Set, which is available in the standard Linux software set. And this was again strong scaling. So now a third thing, if you show the scalings, then everybody will say, yeah, if the code is slow, it scales. So you can make your code slow and it scales really well. But I can show that our code is really fast, and the thing to do in the DG method is you have to look what's the scheme. And the scheme is, so here you have the integral for the flux, and basically what you have here, so G is actually F hat. You have something like the evaluation of the flux for a given set of quadrature points, and here you have the evaluation of the discrete function on one cell. And what's the discrete function on one cell? It's just the sum over all basis functions times some scalar value. So in the end, this looks like a matrix multiplication, and computer scientists know really well how to implement this. So I spoke to some of them, and I did some profiling, and I figured that mainly 97% of my code is dealing with basis function evaluation. So that's really a small portion of the code is taking up a lot of runtime. So it makes really sense to go into that and make that fast. So what I came up with is some sort of automated code generation for only for that part. And after that, it's still 90% of the runtime, but it's a lot faster, and I'll come back to that in a second. So keep in mind that the basis function evaluation of the matrix-free DG method, and that's why I said this in the beginning. So it's matrix-free. That's the point here. The basis function evaluation is taking up more than 90% of the whole computational time. So if you can make that fast, your solver is going to be fast. So that's now I did some what do you call this, efficiency, some flop measurements here on this laptop there, which is a Core i7 Mihalem type with a standard compiler that you probably have to use on the cluster anyway. And the measurement was done with the open source tool called Liquid, which you can just use like user bin time, and it will in the end give you some flop performance numbers. So this is again the density current test case in 3D for polynomial orders 1, 2, 3, 4 on a relatively coarse grid. And what we could see, if we don't do any optimization of the basis function evaluation, we still get ratios like 11 to 16% of the theoretical peak performance, which is really, really good. Many codes can't do that. If we do optimization, we can go up to 25% of the peak performance for the solver. Here on a Cartesian grid. So now, what's it gonna look like on a fully unstructured code? The thing is, on a fully unstructured, it doesn't look much different, because you put so many unknowns in one cell. The unstructured grid really doesn't matter anymore so much. So it really makes sense to use a high order method on the unstructured grids, and you still can have really good or really performant code. So for the k equals 4 case, we have something like 25% of theoretical peak performance. And the thing is, it's an Intel machine, right? I didn't use the Intel compiler, so I guess I can go a bit higher if I use the appropriate compiler and so on and so forth. Okay, so that's basically almost everything I have to say for efficiency and parallelization. On the Blue Gene P, I didn't do these measurements, but I figured if I use this optimized code generation, I get a factor of 2 out of my code, which is really worth it, since it's really a little small, tiny part of the code that I have to optimize. Okay. Oh yeah, I'm running out of time. So another question, and this was a question the weather service guys wanted to know. So if we look into the G method, how good is it compared to what we already have? Does it make sense to use this method? Do we lose much, or do we gain, or what's the thing here? So we did a comparison with Cosmo, which is a finite difference code. It's mostly second order, but for some directions or equations, it's better than second order. It uses advanced IMAX Runge-Kutta scheme with some fancy splitting. The thing is that you have to deal with non-conservative discretizations, which is mostly due to the terrain following grid. So on comparison, the Dune DG version uses a sixth order method here with a third order explicit Runge-Kutta scheme. So you see we have used different time discretizations, which is not the best thing to do. I will come back to that in a second. But we have conservative discretizations, and we can use Cartesian or fully unstructured grids. So again, the density current test case. And what we did for comparison, I think this came up yesterday, and I think we can give some ideas how to compare two totally different codes. So what we did is we compute the solution along this red line here, and then the structure looks like this. And you can see the red one is the Cosmo reference solution, and the green one is the DG reference solution. And you can see they're almost the same. Just here in the third vortex, you have a slight difference. Okay, so they're almost the same. And what we did in the following, so we compute two very fine-grained reference solution, and we compare both schemes to one reference solution, and we compared, of course, to the Cosmo reference solution and to the DG reference solution to be sure that we didn't do anything stupid there. Oh, that was too fast. So what you can see here, we calculated a 200-meter resolution, a 100-meter resolution, and a 50-meter resolution. And the 12.5 meter or the 25 is the reference solution for these three cases. And you can see that, okay, on 200 meter, the schemes do not really well resolve these vortices, but on 100 meter you can see that in blue the Cosmo is doing a bit worse than the DG in green, which can already resolve the three vortices. And on 50 meter, both schemes up to the third vortex can resolve the structure of the solution. So now you got the reference solution, you got the runtime, you do it on the same machine, and then you can actually come up with something like a runtime to error comparison, which is the interesting thing, I guess. And we did this by using the same number of unknowns for both schemes, and what we found was, okay, if I use DG instead of the finite difference, then I have something like a factor of 10. Okay, so the DG method is something like a factor of 10 slower, keeping in mind that for DG we use an explicit splitting and we use a time step that's basically 10 times smaller than the one of Cosmo, so there's a problem. But we also saw that the resolution of the DG scheme is much better if we use the same number of DOFs. So we can use a coarser resolution, and then coarser resolution based on both schemes produce nearly the same error, and what we get then is that, for example, here, so we have that's the 50 meter resolution. The error is 13 for the tune and 14 something for Cosmo, and the runtime is a factor of 3 of that of Cosmo. So that's more acceptable, I say. So given an error threshold, the DG method is 3 times slower in this case than the classical finite difference. Keeping in mind again that the time discretization is not optimal for the DG method. So, and of course what you see here is that at some point, of course, DG will be better since we use the higher order method. But I mean, we are working on this using the same time discretization in Cosmo and in Tune, and then we can come up with probably more promising results. Okay, so for the 2 minutes I have left, I just want to mention the software library or software modules below all that what I just showed, and it is Tune and in particular Tune FEM. So Tune stands for Distributed and Unified Numerics Environment, and development started 10 years ago. So that was when I started my PhD thesis, and it is basically a German project, but now Andreas is in Warwick. So I think also here in the UK, and maybe since I moved to UCAR in October, maybe in the US there will be some people that would like to use this code. So it's a set of C++ modules for implementing grid-based numerical methods. It's an open source code you can download, you can use. It has some parallel things. I mean, as I just said, maybe it's not really ready for the fully adaptive on many cores, but you can do some things.
Here for the dual, we are using the C++. So, is there any specific reason of not using Fortran? The Fortran is supposed to be a, very mature in terms of giving performance for the scientific libraries.
That's not true.
There's just
Not anymore. I mean, it was maybe like 15 years ago or so, but you can achieve as good performance with C++ as you can do with Fortran. The thing is, you have to know what you're doing, and you have to know that in Fortran also. So this really doesn't matter. And you can couple Fortran with C++, so any language you're fine with. I mean, and I think this is not a big problem. And as you just saw, I mean, 25% of peak performance, and it's a C++ code based on an abstract interface. So there are some things that are maybe they were true 10 years before, but not anymore. Okay, so let me just quickly finish. So there are several people involved from Berlin, Heidelberg, and so on, Münster. You can all find that on the webpage. Just maybe one idea to understand what it's like. So it's not really a software package where you have every method implemented. No, it's more like an interface. And the basic idea, for example, for the grid interface is that you have an abstract interface and you base your algorithm or your finite element discretization, you base it only on this interface. And then behind the interface there can be several different implementations that can take care of the specific structure of the grid manager, for example, that you want to implement. And these grid managers can be switched by a compiler flag. So you recompile your code and it all of a sudden runs on a Cartesian grid. You recompile and it runs on an unstructured grid. So this is really easy to exchange. So that's one of the big plus we got in Tune. We got some minus. I won't detail that. So if you look on this webpage, OLO, they have some lists of open source projects, and then they say, okay, there have been 91 man years or person years that have been put into the project, which is worth like 5.5 million euro, and corresponds to an overall of 480,000 lines, and that's just the core modules. So there are a lot of modules around, but the core modules you find on the webpage, that's that. And then the rest of the code has another 300,000 lines, and that's quite something. I mean, I won't say that many lines of code is a good thing, just say there has been quite some work that has been put into that. Okay, the current stable release is 2.2, and I think this came out like a month ago, and this is really mature. Okay, then in Dune Fem, which is a discretization module for Dune, we have some different discrete function spaces like standard, continuous finite element, discontinuous. We have tested some schemes. We have a bunch of Runge-Kutta solvers, of course, available mainly for the DG stuff. We have several linear packages. One is the Tune ISTL. This is the one with the parallel AMG solver. That's really good. We have linked PETSI, which is also really good, I think. You can use umfpack if you like, but that's not parallel. And then some infrastructure that's really necessary for parallel computation, something like checkpointing and data I/O. I mean, how do you do data I/O efficiently on a many-core system? So we did some things there, and I think we can do that quite okay. Okay, that's basically I have to say for today, and maybe just one sentence for discussion. I think that DG methods really allow to efficiently use the supercomputers we have today, and for further things you can look up these two web pages, and thank you for your attention. And I forgot to say one thing. So what I'm interested to work, maybe during the time I'm here and further time, is something like this. So this is the density current test case again. Up here we have the adaptation indicator that Andreas presented yesterday, and down here we have sort of a black box indicator. I won't say that this is really working well, but I mean, that's the black box indicator I could also use for oil equations or other things, and seems to work quite okay. And I would really like to come up with an idea for adaptation indicators that we at least could use. I mean, I've done all this work on making the adaptation work in parallel and so on and so forth, and now I want to use it and I can't because I don't have really good adaptation indicators, and this is really bothering me. So that's one thing I would like to work on. And that's all for today. Thank you.
We are quite over time. Is there, Jürgen, do you want to ask one quick question?
Just a simple one for the comparison of efficiency. How did you define the resolution? So you have more than 1 degree of freedom per cell. So if you have a polynomial of third degree, it's the cell size divided by 4.
The resolution is for the grid is obtained such that, for example, the number of unknowns is the same. So if you have, for the finite difference, you have number of cells is number of unknowns. And then you choose a grid resolution for the DG method such that the number of unknowns is the same as in the finite difference computation. And then, of course, you get a different number of cells. And, of course, not in all cases you can exactly match them. But you get somewhere near. And there's a paper in TCFD which is explaining everything of that, and there's also inertia gravity waves and mountain overflow. So we did not only the comparison for one test case, but for several. And we're planning on doing the comparison for 3D test cases, because 2D is somewhat, it's okay, but you really need to know what's going on in 3D, because sometimes it's really different.
Great, thank you very much. So we'll be back in a bit under an hour's time for the final session.